Hello, welcome again to my lectures on transport. This is going to be the lecture that will direct us to use the finite element method in a practical sense now that we have built a knowledge of how to derive the basic continuum conservation equations. We have derived equations for the continuity of total mass, continuity of species, and continuity of momentum or conservation of momentum, and that led us to the Navier-Stokes equation, and we use this to get the work done on a boundary, and subtracted that or included this in the total energy conservation. And when we did the total energy conservation, we were able to find an equation that describes the change in the internal energy with respect to time. And since this is related to the temperature, C sub V times T, we are able now to describe the evolution of the temperature in the material. That's a heat transfer problem. But if the fluid is moving, then we have discovered that we have a material derivative that has the fluid velocity in it, and we also have terms on the right hand side that represent viscous dissipation and also the work of the pressure that need information on the velocity, which means that we have to couple the fluid equation, the Navier-Stokes equation, and the heat conduction equation if we were to do a solution of a temperature field in a moving fluid. If we don't do that, then we have a static body that can be a solid or a liquid, and this static body, we would solve the same energy equation, which was reduced to a conservation equation for the thermal energy. That equation becomes the diffusion equation. And the diffusion can describe diffusion of temperature, or it can describe equivalently the diffusion of mass or species. So there are modules in COMSOL, and I'm going to review the background first on the diffusion of mass, and then I'm going to review the background on heat conduction, including fluid motion, and then we're going to go to an example that I prepared using COMSOL to see how this is actually implemented. So let's first look at the diffusion of application module. So there is an application module in COMSOL that has specifically for diffusion, and that module here is it solves PDE in this formulation. So the PDE in this module is formulated in a slightly different way than what we discussed. We had dC by dt. Now we don't have any moving fluid, so it's just a static situation, so dC by dt. But this is the multiplied by a time scaling coefficient that can be useful in certain applications. And this is the divergence of the gradient, the divergence of minus d times the gradient of c. And on the right hand side we have here a term that is for the reaction rates that can be nonlinear. For example, if you have gas that is diffusing in the solid and is also reacting at the same time, so you can represent this reaction rate in this module, in this term capital R. So these are described here. You have the time scaling coefficient. D is, if you write it in COMSOL, actually you can write using exactly this script. D, capital D, lowercase t, s, underscore C, it would know that this is actually delta Ts in this equation. Same thing for D, you can write it as D sub C. This is diffusion coefficient for mass. And Dij, if you have an anisotropic diffusion, you can write it this way. So these are kind of conventions within the COMSOL that you can write them down. And then when you go to the subdomain settings in COMSOL, you will notice that you have here the equation is highlighted up here. If it is, for example, no time dependence, then you will have a divergence of minus d grad C equals R. That's all it is. So it's a very simple equation, and you will specify the diffusion coefficient here in this box. If it is anisotropic, then you can put it here in different directions, but if it is isotropic, and you apply it here. So that is done, and then you have to worry about the boundary conditions. What are the boundary conditions in setting up a diffusion problem? We have either a concentration boundary condition, and the concentration boundary condition is you specify a certain concentration at a given boundary. So you have to select on the boundary, which is a domain that I'll show you, and then you specify a particular concentration that you know. For example, zero concentration or a fixed concentration. There is a second type of boundary condition, is a flux boundary condition, and the flux boundary condition is given by an equation that you see here on the left hand side. And this equation, it tells you that you have the equation summarized here, minus the normal vector dotted with the flux of matter, which is minus d grad C. So this is the flux that is actually leaving the boundary, is well, minus n would be entering the boundary rather, is equal to a given known right hand side. So the given known right hand side will be either a fixed value that you know, or you can also specify a rate constant at the boundary, k sub c, times the difference between a background concentration that you know and the concentration at the boundary. These are, for example, when you have a diffusion field like this, and this is the boundary, then there's a rate at which the material can enter, and that rate is dependent on this bulk concentration and the concentration at the boundary. So the difference and gives you a rate constant that would be no. So these are, if you don't have this flux boundary condition, you can use a fixed flux. If the boundary is insulated, then your third option is given by the flux is equal to 0 as a symmetry or insulation condition. For example, if you have an axisymmetric system, and the axisymmetric system, you can show it here as 3 boundaries, and then the fourth boundary, which would be the center of a cylinder, for example, this will be that condition that has actually the flux is equal to 0 on the symmetry for an axisymmetric system. So these are all possible boundary conditions that we can apply. There are additional boundary conditions if you have multi-layer and you have diffusion in multi-layer. And the diffusion in multi-layers is that, for example, across an interface, then you can have the dot product of the normal to the surface times the difference between N1 and N2 will be equal to at this continuity, either continuity like 0 if it is continuous, or n0 when you know there's a jump in the flux, for example. So here's the, let me see that. So we have here n is actually the flux, so we have n0. So using the same symbol here, n1 and n2 is the difference in the fluxes is either equal to 0 or a given value. That's when you have multi-layer. If you have thin boundary layer, for example, then you cannot mesh it, which is very important in some cases because the meshing can become a problem. It's very thin. So we can eliminate that region and we make it a thin boundary layer, and we apply the conditions that the normal type for on the left hand side. So if it is a very thin layer, so you have actually n1 here and you have n2 here, and then the layer is right here. Then the flux on the left and the flux on the right, you can give them the quantities as d over delta. Delta is the width of the or d is the width of this boundary layer, and you know the concentrations on both sides, C1 and C2. And that would be a very nice condition when we have very thin layers that we can use. So that's the diffusion module. Now I'd like to go and describe to you the heat transfer module before we move on to look at COMSOL examples. And the heat transfer module, it follows very similar ideas to what we did, and we have the heat conduction equation in here, and the heat conduction. So what we'll do is we will just look now at the heat conduction equation in a moving fluid and specify what COMSOL uses, what are the symbols that are used in COMSOL, and how we apply the boundary conditions. Because at the end of the day, the theoretical lectures that I gave will have to be translated to either symbols that you put into COMSOL or boundary conditions that you apply, or initial conditions. So it's important that we go through that step by step. So let's now go to this module here. And the module, we have a mathematical model that exactly mimics what we've learned in our last lecture, that rho c sub p dt by d lowercase t minus the divergence of the flux equals to the internal heat source. And COMSOL now has the ability to even include K as a tensor if we have anisotropic heat conduction. And therefore, we can write the previous equation here, this equation, we can write it in a slightly different form, where we have now, if we have convection and conduction, notice that this equation here has only conduction. If we have conduction and convection, which is like in casting, then we would have the material derivative d by dt that I talked about. So the material derivative gives you two terms, d capital T by dt, and then the convected quantity u times the divergence of the temperature. The right hand side remains the same as before. So this will be two variations, either the top one for conduction alone, or the bottom one for conduction and convection. In addition to, if you look at this, we have the equation for the temperature. This is a temperature equation. Then if we want to find the heat flux, if you have convection, it will have two terms, one through conduction, another one through convection. If you have conduction alone, then it will be minus K times the gradient of the temperature. And that's kind of an outcome of the solution. So right now what we're going to do is we're going to discuss the symbolism that is used in COMSOL and the significance of each term and how it is used in the actual implementation. So here, if we have a conduction equation with no convection, then we use a scaling factor, delta TS, that can help in adjusting some time-dependent problems. And you have the density rho C sub p follows pretty much the same symbols that we have discussed in our lectures. Now there are additional features that can be useful. For example, if we have certain domains and these domains have additional modes of heat transfer. For example, we have a domain that has convection heat transfer to the outside, and as we know from Newton's law of convection, that the rate of convection is the heat transfer divided by the heat transfer coefficient times the difference in the temperature, T external minus T, and the dA is a scaling factor. If we have now heat transfer through radiation, it's a difference between the ambient to the power 4 minus the surface temperature to the power 4, and that we have to include this as an additional flux. So it's much richer in the structure, and we could add both convection and radiation on the boundary. So if we look here to the subdomain settings, the subdomain settings, we have all of these quantities that I talked about, and if you write the variable, like for example rho, R-H-O, as an you can actually include an equation of rho to depend on any of the variables inside COMSOL. So you can write rho as a function of T, or as a function of Q, as a function of any T external. All of these are really, you can write them as expressions, which makes it a very powerful method of solution. So having said that, then we can discuss the boundary conditions. The boundary conditions, as you can see here, heat flux boundary condition. The heat flux is N times the normal dotted with K grad T. That's the heat flux, is equal to a prescribed value, or this is a convective value, and or a radiative value. So it's up to you to decide what are these constants here and which ones you want to include. Insulation, the heat flux is 0, prescribed temperature obviously, and again the last one, which is very useful, is when you have a very thin thermally resistive layer, like when you have pair boundaries. So you make a pair of boundaries and you define the temperature on one side and the temperature is on another side, and you get some heat flux across each one of them to connect them. And that's useful in many cases because sometimes we have a very thin layer that's very highly resistive, and if we mesh it, it will be a nightmare to mesh, but we could replace it with these resistive boundaries as well. So that's very similar to what we did in the mass diffusion problem. I think the rest of it is pretty obvious here, and you can read the remainder here, and there's plenty of material for you to just read in the notes. So now what I will do is I'll show you a practical example on this situation using actually COMSOL. So if you look here, I have in COMSOL, I have demonstrated here the actual file that you have here from COMSOL. Let me just turn this off here, and then we'll go to COMSOL itself. So COMSOL itself is, if I bring it here, I'll try to squeeze it into the window for you to see. So I have here a model that I built, and I'll describe to you this model in a second here, once I just get the window to be in the right format. So if I have this, yeah, this is good enough. So this model here that I'll describe to you is the following. I was working on a problem, and in this problem we had a tank head, so it's a very big tank, and it has a head that I had to make. It's a 3D cover, and we wanted to cut an axis hole in the top of the tank head, and then connect to it a coupler, and then do welding to the coupler. So the problem was to do a transient heat transfer during the welding process, and then to recover the residual thermal stresses as the material is cooling down. So it's a kind of a complex project that took a little bit of time for me to finish, but the early part of it, which is a transient heat transfer, is not very difficult, and I'll just explain that to you, and I'll point out how it is actually linked to the solid mechanics module, which has elasticity and plasticity as well. So it's a real nuts and bolts type project for qualification of a tank that is used to transport hazardous materials. So let me just show you the model. So if you go to COMSOL, then you see that you have these tabs, 3 tabs: global definitions. I don't have any global definitions in the model, and I have the model. And the model here, if you click on the left-hand side, the little arrow here, it shows, it opens up a whole bunch of things in the model. So it becomes really big. So if you just close it here, you don't see anything. If you open, then it gives you definitions, geometry, materials, and then you have now other things going on that I'll show you. So let's take one by one. The geometry, you click on the arrow, small arrow, then I imported that from SolidWorks, and this is the geometry that you see on this side here. This is the tank head, and this is the coupler right here. So you can see I can move it around, and it shows you now the features of the coupler on this side, and I need to do a welding operation by adding transient heat flux, because the weld torch is going to go around in a certain manner, and then it will be turned off. Then this whole area is going to heat up, and then it will cool down. So I imported geometry, or you could do it in COMSOL, but it's easier to do it in SolidWorks and import it. And then, so I close this now. I don't have the geometry module. Now the materials. So let me just close this. Materials. I can input materials of will, but in this case, we were using a material called HT9, which is an alloy, a steel alloy. And we were able to input the properties of the alloy in here, and because we wanted to have basic properties for heat transfer, for example, like you can see the density, the coefficient thermal expansion, heat capacity, and these properties have actually expressions, so you can write expressions. And the expressions that you can write will be a function of whatever variable. Here, obviously, these are functions of temperature that you can define. So they're not constant. And then you go to the elastic properties. You have a function of temperature, and then the Poisson's ratio is constant. Elastoplastic material model, now that's took a lot of work. So I'm not going to go through that. This is modeling creep and viscoplasticity, so I'm going to ignore this one for now because it's not for the topic. So now what I have is, so we did the materials, so let me close it. Now we want to do physics. So the physics, you notice that I have a heat transfer module that I selected, and a solid mechanics module also that is here. So if we look at the heat transfer module, you can see its identifier is HT, and the default model is heat transfer in solids, not in fluids. So you can choose solids, and you have domains. Like if you click on 1, then it shows you the green domain, and 2, it shows you the coupler. So I have 2 domains in this heat transfer model. Now I selected heat transfer in solids, not in fluids, and I selected to operate on what? Domain 1 and domain 2. Like you can even have some liquids, some solids. You can do a lot with COMSOL, but here I have it in solids for the 2 domains. Now once you choose the heat transfer module, it comes with thermal insulation on all boundaries. And then you start overriding one by one. Like you see now, if I click this, then this is overridden by something else. This is overridden, this boundary here, boundary 2, boundary 3. So where is boundary 3? You can see it right here on this side here. Boundary 4 is on the back side, and so on. So I have a whole bunch of boundaries there, but they are overridden. Overridden with what? I can put in whatever I need. Initial values for boundary domain 1 and domain 2, both of them I put the initial temperature 293.15. Let me just make sure that when I do thermal insulation, these are boundaries, not domains. So these are the boundaries. Domains is the whole thing. So the whole thing includes boundaries. So the domain includes boundaries. And the boundaries are part of the domains. So we did the initial values, and then we're going to start applying boundary conditions. So the boundary conditions, I chose convective cooling. Where am I going to do convective cooling? On boundary 1, because each one is marked. 2, 3, which is right here, and so on. So what am I doing on these boundaries? I'm using user-defined value for convection heat transfer. You can also have external natural convection or forced convection. But I have here user-defined value, and I did my research. I found that the heat transfer coefficient is good enough to have 40 watts per meter squared K, and that the external temperature is given here, that I put it in. So I have convection everywhere when they do in the welding. Now when they do in the welding, they're welding right here, but the convection is everywhere else. I could have put radiation, but the temperature was not too high or high enough that there will be loss from radiation. So the next step is on these boundaries here, I have to have the input heat, so the input heat flux. So I have to put heat flux boundary condition, and then I choose. You can see number 9 is actually this boundary, the green one here. That is 9. And what is happening on 9, I have a general inward heat flux, and what is it? Is 3E6 times T, and T is less than 60. What does it mean? This is T less than 60 is a logical expression. If it is true, then you get 1. If it is false, you get 0. That's all it is. And then 3E6 is the value of the heat transfer of the heat flux. This is 3 megawatts per meter square. That's 3 megawatts per meter square for 60 seconds. And then you turn it off. So it's a transient problem. And what is happening with boundary 22 is the other boundary, which is on the other side here, is the same. So basically what I'm saying is that they're going around here very fast, but they're putting a heat flux of giving that temperature distribution. I could have programmed it to start from here and give it an angle and then rotate the torch, if there's a torch that is heat flux, and calculate some time dependence of that and put it in here. But I opted not to do that because they go very fast, and therefore it's just maybe within a few seconds you have the welding, and then you turn it off. So that's basically a heat transfer problem that we were discussing. Now just a quick thing here is that you can couple the results of the heat transfer to a solid mechanics problem, where you can solve a linear elastic problem with some free boundary again the boundary conditions. You can put them free and so on. So I'm not going to go through that because I have elasticity, plasticity, but I just wanted to point out that it can be coupled. Now when I look at the study, the next step is to look at the study. What am I doing is I'm studying actually two steps. So I have step one is a time dependent. So you choose time dependent. You give it the range of the time from 0 to 1 with a step increment of 0.1, and you study it on geometry 1. And then what you activate, you physics select, you select the heat transfer module by itself, because I didn't want to do time dependent solid mechanics because that includes vibration. So if I used it, then the solution would have taken forever, and I don't need to really worry about vibrations while they do the welding, because it'll be very minimal. So I just do the heat transfer by itself in this phase in step 1, and once step 1 is done, then I do step 2, which is the next step, and here you see the X marked, the heat transfer is marked X, and I activated the solid mechanics because it picks up from the solution, time-dependent solution of the heat transfer, and it does not a time-dependent solution but a stationary solution, and meaning that it doesn't have the inertia terms in it, so it doesn't have vibrations, but it gives you evolution of the stresses as a function of time. Here's the results. The results, you click here, so we did the study. Now we are going to look at the next section, which is the results. The results, you can do 3D plots. You can choose so from which solution, 1 or 2, and you can choose the time at which you want to have the plot. And what are you viewing here? This is surface temperature, and you can see the surface temperature at 0.2 seconds is very hot on here, but it still hasn't penetrated much into the solid. And you can just continue that and choose different times, and it'll give you, like, you know, just you can even make a movie out of this. You can also do a slice to give you contours of temperatures at different locations in the system. So I think with that you have a very good idea about the conservation equations that we study in our course. Not only that, but you have good initial thinking as to how to use it in practical sense with COMSOL. The only thing that you need to do is practice a little bit on the geometry, so you can introduce the geometry by either importing it from SolidWorks or by doing it actually on COMSOL, and that you can look online for some tutorials on how to do the geometry itself. I'm going just to show you the geometry and how it's meshed here, and if I show you this, then it will be under the mesh, and the mesh would show you as you can see here. So this is it's a fine mesh that is done automatic. If you want to to do the solution for this, it's going to take a long time, but you can actually make it different kind of mesh if you want. You can change the size, and instead of fine, you can make it coarse. For example, if you have coarser, then you click here, and then it will rebuild the model, and it gives you a coarse mesh, as you can see in here, and so on. So you could also play with initially you can solve the model. You can solve the model with the coarse mesh, and then after you solve it and you get some results, then your final results, you can make it finer. You can make the mesh finer and run it again and get more accurate conclusions from your simulations. And I think that's a pretty good introduction to COMSOL, and I hope that you'll be able to use it in your class. And also probably this will be great for you for other classes as well. We'll see you in the next lecture.